Hey there, fellow explorers. Have you ever wondered how Google finds exactly what you're looking for among billions of web pages? Or how Netflix seems to know your taste in movies better than your best friend? The answer, my friends, lies in the fascinating world of data structures and algorithms. These aren't just fancy terms programmers throw around. They're the invisible engines powering our digital world. Just like a car engine, we might not see it, but we sure experience the results. In this exciting journey, we'll unravel the mysteries of data structures and algorithms, making them clear and fun for everyone. Get ready to discover the building blocks of computer science and how they shape our online experiences. We'll explore different ways to organize information, just like arranging books on a shelf or ingredients in a recipe. We'll also learn about the step-by-step instructions that make computers tick, much like a set of directions guides us to a destination. So buckle up, and let's dive into this amazing world together. Imagine you have a giant Lego collection scattered across your room. It's a mess, right? You can't find the pieces you need, and building anything becomes a frustrating task. That's where data structures come in. They're like storage containers for information, helping us organize data in a way that makes it easy to find and use. Just like sorting your Lego bricks by color, size, or type, data structures help us categorize and manage data efficiently. Think of a bookshelf. You can arrange books by genre, author, or size. This organization makes it simple to locate a specific book when you need it. Similarly, data structures provide different ways to organize data in a computer's memory. We have arrays, which are like numbered boxes holding a sequence of items. Each item can be accessed quickly using its index. Arrays are great for situations where you need fast access to elements, but they have limitations when it comes to inserting or deleting items. Linked lists are like chains where each element points to the next, allowing for flexible insertions and deletions. They are ideal for scenarios where the size of the dataset changes frequently. Now, let's talk about algorithms. They're like blueprints or recipes that tell the computer how to solve a problem step by step. Algorithms are essential for performing tasks efficiently. Just like a recipe guides you to bake a cake, an algorithm guides the computer to perform a specific task, such as searching for information or sorting data. For example, sorting algorithms arrange data in a particular order, making it easier to work with. Efficient algorithms are crucial for speedy performance. They ensure that tasks are completed in the shortest possible time, saving both computational resources and time. Imagine searching for a word in a dictionary by flipping through every single page. It would take forever and be highly inefficient. That's why we have algorithms like binary search, which smartly divides the search space in half with each step, making the process much faster. By repeatedly narrowing down the search area, binary search quickly zeroes in on the target value, demonstrating the power of efficient algorithms in problem solving. Let's explore some common data structures that programmers use every day. These structures are fundamental to efficient coding and problem solving. Arrays. Imagine a row of mailboxes, each with a unique number. That's an array. It stores elements in contiguous memory locations, making it super fast to access any element using its index. Arrays are particularly useful when you need to store a collection of items of the same type and access them quickly. Linked lists. Picture a treasure hunt where each clue leads to the next. Linked lists work similarly, with each element pointing to the next one in the sequence. Unlike arrays, linked lists do not require contiguous memory locations, which makes them more flexible in terms of memory usage. This structure is great for inserting or deleting elements without shifting the entire list. However, accessing elements in a linked list can be slower compared to arrays because you have to traverse the list from the beginning. Stacks. Think of a stack of plates. You can only add or remove plates from the top. This last in first out (LIFO) principle is what defines a stack. Stacks follow the last in first out (LIFO) principle, making them useful for tasks like undoing actions or managing function calls in programming. They are also used in algorithms for depth-first search and for parsing expressions. Queues. Imagine a line at a ticket counter. The first person in line gets served first. This is the first in, first out, FIFO principle. Queues follow the first in, first out, FIFO principle, making them suitable for managing tasks in the order they arrive. They are commonly used in scenarios like task scheduling, handling requests in web servers, and managing print jobs. Trees. Think of a family tree with branches and leaves. Trees are hierarchical structures with a root node and branches connecting to child nodes. Each node can have multiple children, making trees ideal for representing hierarchical data. They're used for representing hierarchical relationships, like file systems or organizational structures. Trees are also fundamental in databases and for implementing efficient search algorithms like binary search trees. Graphs. Imagine a network of cities connected by roads. Graphs consist of nodes, vertices, and edges, connections, representing relationships between objects. They are versatile and can represent various types of relationships. They're used for social networks, maps, and recommendation systems. Graphs are also crucial in algorithms for finding the shortest path, network flow, and in many other applications. Hash tables. Think of a dictionary where each word is associated with a specific page number. Hash tables use a hash function to map keys to their corresponding values, allowing for efficient searching and retrieval. They are particularly useful for implementing associative arrays, database indexing, and caches. Section 4. Step-by-step solutions. Understanding algorithms. Now that we've explored data structures, let's dive into the world of algorithms. Algorithms are the heart of computer science, providing step-by-step instructions to solve problems efficiently. Here are some fundamental algorithms and how they work. These algorithms are the building blocks for more complex operations and are essential for any programmer to understand. Sorting algorithms. Imagine arranging a deck of cards in order. Sorting is a common task in programming, and there are various algorithms to achieve it. Sorting algorithms, such as bubble sort and merge sort, arrange data in a specific order, like ascending or descending. Each has its own method and efficiency. Bubble sort repeatedly compares adjacent elements and swaps them if they're in the wrong order. It's simple, but can be slow for large datasets. Merge sort, on the other hand, divides the list into smaller sublists, sorts them, and then merges them back together. This makes it more efficient for larger lists. Searching algorithms. Think of finding a specific book in a library. Searching is another fundamental task in computer science. Searching algorithms, like linear search and binary search, help us find a specific element in a data structure. Each has its own approach and use case. Linear search checks each element one by one until it finds the target. It's straightforward, but can be inefficient for large datasets. Binary search, on the other hand, requires a sorted list and repeatedly divides the search space in half, making it much faster for large datasets. This efficiency makes it a preferred choice for many applications. Traversal algorithms. Imagine exploring a maze. Traversal algorithms help us navigate through data structures like trees and graphs. Traversal algorithms like depth-first search, DFS, and breadth-first search, BFS, systematically visit every node in a tree or graph. These algorithms are crucial for tasks like searching and pathfinding. DFS explores a path as far as possible before backtracking, making it useful for scenarios where we need to explore all possibilities. BFS, on the other hand, explores all the neighbor nodes at the present depth before moving on to nodes at the next depth level, making it ideal for finding the shortest path in unweighted graphs. Section 5. Algorithms in action, real-world applications. Data structures and algorithms are everywhere in our digital lives. Here are some real-world examples. Google Search. Google's search engine relies heavily on algorithms to index billions of web pages and deliver the most relevant results based on your search query. They use complex algorithms like PageRank to determine the importance and relevance of web pages. Social networks. Social media platforms like Facebook and Twitter use graphs to represent connections between users. Algorithms analyze these graphs to recommend friends, suggest content, and target advertisements. E-commerce recommendations. Online shopping sites like Amazon use sorting algorithms to display products based on relevance, price, or popularity. They also use recommendation algorithms to suggest products you might be interested in based on your browsing history and past purchases. GPS navigation. GPS navigation systems use algorithms like Dijkstra's algorithm to find the shortest path between your current location and your destination. They consider factors like distance, traffic conditions, and road closures to provide accurate directions. The journey of 1,000 lines of code begins with a single step. Whether you're just starting out or looking to deepen your understanding, remember that every expert was once a beginner. Keep exploring, keep coding, and keep pushing the boundaries of what's possible. Your journey in the world of